So, what we see from the expression we had earlier is that we see that P v is equal to m into r into T, where r is the specific gas constant. This is possibly the most common way in which I am going to use this expression. You can use it in any way you like. So, what we see is that P v by T, if I have a system which has a gas of a fixed mass, which is my definition of a system anyway, that the mass has to be fixed. So, if I have sorry about that, if I have PV is MRT and I take the T over here, R is a constant for a gas. So, if I have a gas whose composition is not changing, R is constant. If I have a system, then the mass is fixed, so M is constant. So, what I see is pressure into volume by temperature is constant. So, this is what I see, because this entire thing is essentially a constant. A consequence of this is that the internal energy U is only a function of temperature, and enthalpy H is also a function only of temperature. So, we can possibly look at some examples of how we can find out the change in internal energy, but for the time being we can just look at how we can quickly find out this also. So, for example, if I have a certain system of this kind which has a certain mass of some ideal gas, yes, an ideal gas over here. Let us say I add some heat to this process, to this system. The system itself is rigid, so it does not undergo any deformation. The system is placed on some support, it is not moving, there is no change in no change in kinetic energy of the system. It is on some base, it does not move anywhere, there is no change in potential energy of the system. I can apply the first law of thermodynamics to the system. So, the first law for the system undergoing a process, we said that the first law can be given in this form. And we also saw that for a simple compressible system, this del W is given as some P dV, because the only form of work which we are considering for a simple compressible system such as a gas is that there can be work done because the system expands or contracts. So, in general that would be given in this fashion. Now, in this particular system which I have over here, we see that the system is rigid, which means there is no change in the volume of the system has a fixed volume. So, therefore, dV is 0, because dV represents change in volume. If it is a rigid system, dV does not change, so this is 0. So, I have del Q is equal to dE. We said earlier that we can separate out this dE as du plus change in kinetic energy plus change in potential energy, which is what we have. So, what we see is that this is also 0, because this system is fixed, it is not moving anywhere. Similarly, this is also 0. So, what we see is that any heat transferred must go into changing the internal energy of this system. Okay. So, what we can also define is we can define the specific heat of a system. So, the specific heat is we call it as either Cp or Cv, and the specific heat is the amount of heat I need to give to change the temperature of a unit mass of system by a unit value. So, for example, over here I am considering a system which has a fixed volume. So, the specific heat is defined as the amount of heat I need to give for changing the unit mass by unit temperature. So, this is how I would define it, and so what I see is del Q is du over here. So, which means that du by dt into 1 by m is equal to Cv, or I can see that du is equal to Cv into dt into m over here. So, my mass is fixed, and what I see then is that du is a function of Cv and dt. So, if I have Cv as a constant, then the internal energy must be a function only of temperature. That is also something which I see. So, the internal energy per degree of freedom in a gas from kinetic theory is equal to half into kT under equilibrium conditions. The degree of freedom refers to how many ways in which this molecule is free to move. It can be either translational, rotational or vibrational motion of a molecule. And K over here is the Boltzmann constant given as the universal gas constant divided by the number Avogadro number, okay, which is essentially 6.023 in 10 to the power 26 molecules per kilomole. We are usually more used to writing this in terms of 23 molecules per mole, but to be consistent with the remaining units, it is written here as 26 molecules per kilomole. And the number of degrees of freedom, if we can specify it as say d, then internal energy per molecule is essentially half into k into t, because as we said over here, this is for each molecule it is equal to this. So, if I have 1 kilomole of molecules, it is essentially given as this form, Avogadro number into d into kT by 2, and from our definition earlier of k, this comes out to be d into RT by 2. So, similarly, this is for the internal energy. Similarly, for the molar enthalpy, we know that the enthalpy is U plus PV. So, when we have in mass terms, this is an internal energy in units of joules, and we have PV where V is in meter cube. When we have it in molar terms, this is for like say when we have mkg, this would be the value. If we have so many moles, then the molar enthalpy is given as H bar, which is U bar, which is the specific molar enthalpy plus pressure times the specific molar volume. So, it is given in this fashion U plus PV, and we know from the previous slide which we had that PV is equal to R bar into T, where this we had this N, we divided V by N and we got V bar, which is the specific molar volume. So, we can instead of PV bar we can write it as R bar T, which is what we get. So, we have U, which is d into RT by 2 plus RT, R bar T, sorry, this also is R bar over here. So, which essentially gives us d plus 2 by 2 into R bar T. This is the specific molar enthalpy. Similarly, the specific molar internal energy is given as d into R bar T by 2. So, we can also write these in terms of the molar specific heats. So, here we write it as U bar is equal to Cv bar times T. So, which is d into R bar T by 2, where of course, whatever is there in front of the is essentially whatever is in front of the T is essentially Cv bar, which is essentially this d R bar by 2. Similarly, for enthalpy, whatever was in front of the T is what we write as Cp. So, which now comes out to be d plus 2 into R by 2. In this case, of course, the units will be joule per kilomole. If we are writing it in terms of just the molar values, you will have it like this, and we can look at specific internal energy and specific enthalpy, where we divide U by the number of molecules, essentially we divide by the molecular mass. So, d into RT by 2 divided by m you get. So, essentially we get Cv is d into R by 2, okay. And similarly we can get the enthalpy where we get Cp is d plus 2 into r by 2. What we have done is we have taken this m over here and we have taken the r bar and we are left with r. So, that is essentially what we have here. Sorry, this I think an r bar, this r bar is already there, this was missing. So, we should have that as well, and there is an r bar over here which seems to have gone missing for some reason. So, this r bar by m is essentially our r. So, this is the universal gas constant, this is specific gas constant, this is the universal gas constant, and again this is the specific gas constant. So, having these formulae for the specific heats, what we can do is we can divide them to find out the ratio of specific heats, which is what we call usually as gamma. So, gamma is, we can either call it as Cp by Cv, which is also equal to Cp bar in molar terms divided by Cv bar, does not matter, both are the same. So, there are some bars over here which are again missing. So, it is either ratio of molar specific heats at constant pressure and constant volume, or specific heats on mass basis at constant pressure and constant volume, which give us this expression, which is essentially d plus 2 divided by 2. So, this is how we find out the specific heat of a ratio of specific heats of an ideal gas, So, this d we said is the number of degrees of freedom. So, if we look at a diatomic gas, so it has like say 2 molecules, let us say it is 2 molecules connected in this fashion. If we have at low temperatures, then what we can see is that this molecule has 3 translational degrees. So, it can move along the x axis, along the y axis, or along the z axis. So, it has 3 translational modes of freedom. It can also rotate about 2 axes. So, it can rotate about this axis in this fashion, or it can rotate about out of the plane of the paper in this fashion. So, it can rotate about 2 axes. Rotating about the bond in this way does not have much energy in rotating about this. What it can do is it can rotate about like this. If these are the 2 ends, it can rotate like this, or it can rotate like this. So, those are the 2 rotational degrees of freedom. So, it essentially has 5 degrees of freedom. So, what we are ignoring is that the fact that this can also move outward and inward. That like if you consider this as like say 2 balls connected by rubber band, we are ignoring the fact that you can stretch the rubber band or bring it together. So, that is not being considered, because that is not significant when you have low temperatures. So, under these low temperatures, it has 5 degrees of freedom, and if we now put these values over here, we get the value of gamma. Similarly, if you have a monoatomic gas, it has 3 degrees of freedom, which it can move in x, it can move in y, it can move in z. It does not matter if it rotates on its own, because you cannot really make out the difference. So, it can only move in these 3 directions. So, it has only 3 degrees of freedom. So, we had over here, for example, nitrogen gas, which is a diatomic molecule. What we can try to do is find out gamma for this gas. So, we see that gamma is essentially d plus 2 divided by d. Nitrogen is a diatomic gas, it has 5 degrees of freedom. So, d is 5. So, we have 5 plus 2 by 5, which is essentially 7 by 5, which is 1.4. So, we see that for nitrogen the gamma value is about 1.4, which is also the same value for all diatomic ideal gases, provided the temperature is not too large. In a similar fashion, we can also do this for like say monoatomic gases. So, gamma in this case would be again d plus 2 by 2, but we have d as only 3, because they can only move in x, y or z, it does not have anything to rotate about. So, this would be essentially something like this, because d is 3. So, which has a value of about 1.67. What we can now try to do is also find out what is the relation between R and Cp and Cv and so on, which is what we are going to do. So, we have our expressions. The enthalpy is defined in this fashion, it is U plus PV. We are looking at specific enthalpy, specific energy, specific volume, U plus PV. From the definition of an ideal gas, we saw that PV is equal to mRT, or we saw that if I divide by m over here, PV is equal to RT. So, from a definition of my ideal gas, I get this is equal to U plus RT. U remains as it is, instead of PV I can replace it by RT. So, enthalpy into temperature is the amount of heat which would be transferred if I have a constant pressure process. So, CPT would be the enthalpy, which is given, and U is essentially CVT, and I have RT. So, if I now cancel out the temperatures over here, I get Cp is equal to Cv plus R as a relation between Cp, Cv and R, or if I want to rewrite this, I get Cp minus Cv is equal to R, which is what we are more commonly used to writing. Over here, if the units of Cp and Cv are in joules per kg Kelvin, then R would have the units of joules per kg Kelvin. If I am using molar specific heats and I have units of Cp and Cv as joule per kilomole Kelvin, then R would also have units of joule per kilomole Kelvin, and then it would be the ideal the universal gas constant. So, we have this expression here already. What we can also find out is gamma, which is essentially Cp by Cv, and using this formula and substituting in the expression for gamma, what we see is that we can instead of Cp plus Cp by Cv, I can put Cv plus R by Cv. The Cv gets cancelled, I get 1 plus R by Cv. So, gamma is 1 plus R by Cv, which means that gamma minus 1 is R by Cv, which means Cv is R by gamma minus 1. This is a relation which we get between Cv and R. Again, if I am using R as a specific gas constant, units of R is joule per kg Kelvin. So, Cv also has the same units. If I have R as a universal gas constant, then I would get the specific molar Cv. So, if I use R as R bar, I would get Cv as Cv bar. So, since Cp by Cv is gamma, so once I know Cv, I just have to multiply by gamma to get Cp. So, Cp is gamma times this, so it is gamma by gamma minus 1 times R, and same as before, if I use specific gas constant, I get specific heat at constant pressure. If I use universal gas constant, I get the specific heat on a molar basis. So, knowing this, what I can do is I can calculate R, Cp and Cv for nitrogen. So, I know the ratio of specific heats for nitrogen, it is a diatomic gas, this is the value. I can find out R, the specific gas constant is R, which is essentially R bar by m. So, I know that R bar is 8314.5 joule per kilomole Kelvin, and m for nitrogen has a value of 28 kg per kilomole. So, the kilomole cancel, I will get joule per kg Kelvin as the answer. So, I get 8314.5 by 28, which I am going to find out the value of. Which gives me a value of about 296.9 joule per kg Kelvin. I can find out Cv, which has the value of R by gamma minus 1. So, I have the value of R, gamma I have already found out, it is about 1.4. So, if I find out the value of Cv, so R divided by 1.4 minus 1, that is R divided by 0.4, which has the value of about 742.3 joule per kg Kelvin. For finding out the value of Cp, I can either add these two, or I can also multiply gamma times Cv. One of these two is what I can do, which has the value of about 1039 joule per kg Kelvin. The Kelvin of course is in the denominator in both the cases. I am writing it without the bracket, assuming it is understood, but maybe I should put brackets here so that there is no confusion. This is just kilomole, so that is not a problem. So, I can find out values of R, Cp and Cv in this fashion for any gases which I want to do. What we see is that the number of degrees of freedom which a gas has can change, because at higher temperatures what happens is vibrational modes get excited. So, the molecules do not stay at, so if I have a molecule with 2 atoms, diatomic molecule, the 2 atoms I am assuming are at the same distance from each other, but at higher temperatures they can vibrate. So, these molecules can move apart and come back closer, and more energy gets stored in that kind of a fashion. So, the vibrational mode gets excited. Therefore, what it happens is that the fractional number of molecules with vibrational excitation will increase as you go up in temperatures, which means that the degrees of freedom will change, because there is more energy stored in that kind of a movement as well, and therefore, gamma, Cp and Cv also will change as the temperature changes. So, what we said so far is that the formula we wrote, saying d plus 2 by d is the gamma, that is not true at higher temperatures.